Section 7.4, Hypothesis Testing for Proportions. As I said in the last chapter, often we use proportions because we have no relative scale of how big or how something small is. So we look at a percentage or the decimal point of it, basically. We almost do the same type of tests, except some of the factors are a little different. We're still comparing the sample mean to the population mean, dividing by a standard deviation, and then seeing if it falls within a certain alpha. We're also stating our null and alternate hypothesis. However, when we have proportions, what we're going to do here is look at the p-hat, which is the sample proportion, versus the population proportion, which is the p right here. And we'll be seeing this in the next few pages. Here's my p-hat, my sample proportion. Here's my population proportion. And then we divide that by the square root of the sample proportion p times q, which is 1 minus p. We multiply that together and divide by number of samples, take the square root of that. So when we do this, we're going to compare this to where it falls within the alpha. This gives us our how many deviations it is. Let's go through some examples here. A researcher claims that less than 45% of U.S. adults use passwords are less secure because complicated ones are too hard to remember. In a random sample of 100 adults, 41% said they use passwords that are less complicated because complicated ones are too hard to remember. Alpha 0.01 is enough evidence to support the researcher's claim. Well, the research claiming that less than 45% of adults use passwords are less secure. So it's a less than, which means that is under the alternate hypothesis. And it's one-tailed since it's pointing to the left. It's left-tailed, which means the null has to be greater than or equal to, and there's our equality statement right there, the greater than or equal to. It's greater than or equal to 45%. I got an alpha 0.01. And when I look up alpha at 0.01 on my sheet here, since it's left-tailed, I'm using the negative side. 0.01, the closest it comes to is 0.0099, which is negative 2.33. So my make or break area is negative 2.33, and there's my line right there. Anything over here, I'd reject. To the left of that, this is left-tailed. Anything to the right of that for my z-score, I would fail to reject. So let's look at this here. Set it all up. My sample proportion I did, my p-hat, is right here at 41%. So 41%, my p-hat, minus 45%, my population proportion, is minus 0.04 or minus 4%. In my denominator, I've got the square root of 0.45, which is my population proportion, that's my p, and then my q is 0.45 subtracted from 1, which is 0.55, and that's divided by 100 because we did 100 samples. When I do the calculation, 0.45 times 0.55 divided by 100, the square root of that is 0.04975. Negative 0.04 divided by 0.04975 is negative 0.804. 0.804 is right here. It's in the fail to reject region. It is greater than negative 2.33, which is where my alpha was. So I had failed to reject the hypothesis, and I cannot support the claim. Here's another example. A researcher claims that more than 90% of U.S. adults have access to a smartphone. In a random sample of 150 adults, 87% say they have access to a smartphone. Alpha 0.01 is there enough evidence to support the researcher's claim? Well, I hear right here that it's more than 90%. That is what the claim is, and that is an inequality, more than 90%. So it's on the alternate hypothesis, that's what the claim is, greater than 90%. And Since that's pointing towards the right, it's one-tailed and it's right-tailed, as I've shown here. If it's greater than 90%, then the null hypothesis has to be less than or equal to. There's the equality statement. Alpha is 0.01. And as we did before, alpha at 0.01 is 2.33. Let's find that out to make sure. And there it is on this side. 2.33 is on this side 0.9901. 0.99 plus 0.01, which is what we're looking at here, is at 1 or 100%. So I had a negative 2.33 here, and that's where we got the 0.01 on the other side. But remember, it's symmetrical, so this will be actually plus 2.33. So anything to the right of 2.33, I reject. Anything to the left, I fail to reject. And F are there. So when I'm doing this, let's do my calculation. It's a proportion. My sample P, or my P hat, I should say, is 87% right here. Population proportion is 90%. 87 minus 90% is negative 3% or 0.03, as I got right here. In my denominator, I take the square root of the population proportion, P, times the Q, which is, if P is 0.9, then the Q is 0.1. Remember, P plus Q equals 100%, or 1 minus P is Q. And that's divided by number of samples is 150, as it says right here. 0.9 times 0.1 divided by 150, the square root of all that is 0.0245. Negative 0.03 divided by 0.0245 is negative 0.1225, way to the left here. And since that is to the left of my break rate, 2.33, we would fail to reject the null hypothesis. So we can accept this right here. We cannot support the claim. Now, another thing you should know is if they do not give you what the P is, you can figure it out by yourself. The P hat, I should say, is the samples divided by the given the answer you want, or your success rate, or P, divided by total number of samples. Let me show you right here. Researcher claims that 51% of U.S. adults believe incorrectly that antibiotics are effective against viruses. In a random sample of 2,202 adults, 1,161 say antibiotics are effective against viruses. At alpha 0.10, is there enough evidence to support the researcher's claim? Well, let's see what our P hat is. They don't give it to us. But our sample survey says 1,161 believe antibiotics are effective against viruses out of 2,202. 1,161 divided by 2,202 is 0.527. So that's our P hat. Now let's see. Research claims that 51% of adults believe, and it's an exact amount of 51%. So that is the null hypothesis, P equals 51%. Which means the other hypothesis is the inequality statement, P is not equal to 51%, and they give us an alpha 0.1. So when I look at 0.1 here for the alpha, I'm going to find my critical points here. And 0.10, and this is two-tailed, by the way, so this is equal or not equal, is, let's take a look at this here. Remember, if it's 0.1, that's 0.05 on both sides. So that means on the very left, it's 0.05. And let's see what 0.05 is, the closest it is to it. And that would be right here. We've done this before. It's right between 0.0505 and 0.0495, which is negative 1.645, right between the 0.04 and 0.05. So that's our left side, which means our right side, since it's symmetrical, is plus 1.645. And we can also find it right here. It's 0.9495 and 0.9505. That's 95%. So it's 0.05 on the other side, and that's my plus 1.645 right between those two. So anything less than a z-squared negative 1.645, I'd reject. Anything to the right of plus 1.645, I'd reject. And anything between those, where my blue is marked up here, I'd fail to reject, or you could say I accept it. So let's take a look at this. Now we got our p hat, which we figured out on our own. We got 0.527 up here. 0.527 minus the population mean 0.51 gives 0.017. And then in my denominator, 0.51 is my population proportion times my Q, which is 1 minus the population proportion, 0.49. And my total number of samples is 2022. So 0.51 times 0.49 divided by 2022, square root of that, gives me 1.59. And 1.59 is less than negative 1.645, greater than negative 1.645. So I would fail to reject the null hypothesis. So I would say I can reject the claim because I'm an alternate, and I fail to reject the null hypothesis. Here's another similar problem. A researcher claims that 67% of U.S. adults believe that doctors prescribing antibiotics for viral infections for which antibiotics are not effective is a significant cause of drug-resistant superbugs. Superbugs are bacteria that are resistant to many or all antibiotics. In a random sample of 1,768 adults, 1,150 say they believe doctors prescribing antibiotics for viral infections for which antibiotics are not effective is a cause of drug-resistant superbugs. An alpha 0.10 is enough evidence to support the researcher's claim. Now, we're not given a p-hat, a sample proportion, but we can figure it out because where it's given here. There were 768 adults that were surveyed. 1,150 said they believe that the doctors prescribing antibiotics for viral infections is causing superbugs. So 1,150 divided by 768 is 0.651. That's our p-hat, or our sample p. On null hypothesis, a researcher claims that 67% of U.S. adults, that's the claim, and it's equal to, doesn't say less than or at least or most or a minimum, so it's equal to 0.67 or 0.67, which means the alternate has to be the inequality statement, which is not 0.67. And since it's equal and not equal, that's a two-tail. Alpha is 0.10, which means 0.10 split among the two tails is 0.05 on each side. We just did this previously, and that would actually be negative 1.645 right here, and 1.645 right between these two for negative, and then on the flip side, plus 1.645 right between these two. So I'd reject it if it's less than 1.645 or greater than plus 1.645. Anything in this, I fail to reject. So let's do our analysis to see if we would reject this claim or fail to reject it. Sample P is 0.651, which we figured out, my p-hat. My population P is 67%. 0.651 minus 0.67 is negative 0.019. In my denominator, my P is 0.67, which means my 1 minus P or my Q is 0.33. 0.67 times 0.33 divided by number of samples, 1,768. That gives me 0.0112. And when I divide negative 0.019, 0.0112, I get negative 1.70. And 1.70 is below negative 1.645 right here. So I would reject the null hypothesis. Ultimately, I reject the claim.